Hi, my name's Amanda and I'm a pharmacist. This is my full video presentation series of pharmacy technician math calculations to help prepare for the PTCB pharmacy technician certification exam. It includes 10 lectures combined into one video for your convenience. And as always, if you find this video useful, please like, share, and subscribe. And if you'd like to support this channel with a donation, press the heart thanks button to give me a super thanks. Thanks, I really appreciate it. The pharmacy technician math calculation lectures in this video include basic math skills, ratios and proportions, conversions, days supply, concentrations, dilutions, alligations, IV flow rates, temperature conversions, and weight-based dosage calculations. I hope it's helpful. Hi, my name's Amanda and I'm a pharmacist. Today I'll be talking about basic math skills for pharmacy technicians. We'll be covering fractions, decimals, and percentages. And if you find this video useful, please press the like button, subscribe to my channel, and share it with others who may find it helpful too. Thanks, I really appreciate it. So basic math skills are the building blocks for solving a variety of pharmacy calculations. This includes fractions, decimals, and percentages. So we'll begin with fractions. So what is a fraction? A fraction is a portion of a whole indicated by division of the whole into equal parts. So for example, 1/4, it can be written as 1/4 or 1/4, and sometimes that will be said 1/4, or as I said, 1/4. So 1/4 means one of 4 equal parts. So you can see I have a pie shape here, and we have one of the parts shaded. It's divided into 4 equal parts and we have one part shaded. So one of the 4 equal parts, that would be 1/4. So the top number of a fraction, that is the portion of the whole, and it's called the numerator. The bottom number of a fraction, that is the whole, and it is called the denominator. So for our example of 1/4, 1 on the top is the numerator, and that is the portion. And 4 on the bottom, that's the denominator, and that's the whole. So here's another pie to look at. So what fraction of this pie is shaded? And the answer is 2/4. So 2 of the 4 equal parts is what's shaded. So 2/4 means that there are 2 equal parts which are worth 1/4 each. So now we'll talk about equivalent fractions. A fraction can be changed to an equivalent fraction by multiplying or dividing the numerator and denominator by the same number. So for our pie that we just had, the example of 2/4, if we divide the numerator and the denominator each by 2, 2 divided by 2 equals 1, 4 divided by 2 equals 2. So that equals 1/2. So 2/4 is equal to 1/2, and you can see that with our pie. It's 2/4, but also if you're looking at it as halves, there is 1/2 of it shaded. So now we'll talk about when a fraction has an equal numerator and denominator. So we have our pie again in the 4 pieces. Each piece is worth 1/4. So if we add our fourths, we have 1/4 plus 1/4 plus 1/4 plus 1/4. That equals 4/4. So we have an equal numerator and denominator. And when we have that, that is always going to equal 1. So 4/4 equals 1. So we have 4 out of the 4 pieces. That's going to be 1 whole pie. And you can see the numerator and denominator are equal. Now we'll talk about improper fractions. So when the numerator and denominator are equal, the fraction equals 1, which we just saw on our last slide, for like 4/4 equals 1. Now when the numerator is greater than the denominator, the fraction is going to be greater than 1, and this is known as an improper fraction. For example, 5/4, 5/4, it is equal to 1 1/4. And you can see if we have 5/4 here, we're going to have 1 whole pie, which is 4/4. Plus 1/4 of another pie. So that's 5/4. It's an improper fraction. We can convert it to its whole number and the fraction that's remaining, which will be 1 1/4. So now we're going to talk more about the definition of a fraction, look a little closer at that. So a fraction is a portion of a whole indicated by division of the whole into equal parts. So the line separating the portion and the whole of a fraction, it means to divide. So per means to divide. Remember I said one of the ways to say like a fraction like 1/4 is 1 per 4 or 1 over 4, but per means to divide. So for example of 1/4, 1 over 4, 1/4 equals 1 divided by 4. And if we solve that with a calculator or working out the division problem, that equals 0.25. So 0.25 is what 1/4 is in decimal form. And we'll talk a little more about that when we get to our decimal section. So we'll look now at some fraction and decimal equivalents. These are common ones that you may see. 3/4 equals 0.75. 1/2 is 0.5. 1/3 is 0.33. 1/4 is 0.25. 1/8 is 0.125. Now it's not necessary to memorize this because they can easily be calculated by dividing, but these are helpful to know, especially if you aren't familiar with fraction and decimal equivalents. Now we'll look at a whole number when it's written as a fraction. So since a fraction means to divide, to write a whole number as a fraction, we just simply put it over 1. So for example, the number 4 written as a fraction would be 4 over 1. And you can see that that makes sense because 4 divided by 1 is 4. And we know that the fraction line means to divide. So 4 equals 4 over 1. And this is a very important concept to know for pharmacy conversion calculations. And you'll see that in some of the other math videos I've done about how we put a number over 1 to set up a conversion. Now we'll look at multiplying fractions. So fractions are often multiplied in pharmacy conversion calculations. So to multiply fractions, first we're going to multiply the numerators across. Remember that's the top number. And then we're going to multiply the denominators across. That's on the bottom. And then we're going to reduce the new fraction to its simplest form. So for example, if we have 3/4 times 2/3, we're going to multiply the top across, the numerators. 3 times 2 is 6. And then we'll multiply the denominators across. 4 times 3 is 12. And so we get 6/12. Well, that's not in its simplest form because we know that both of those numbers can be divided by the same number. And the highest number that they can be divided by is 6. So 6 divided by 6 is 1. And 12 divided by 6 is 2. So that equals 1/2 in its simplest form. Okay, so that's finishes fractions. Now we're going to look at decimals. So a decimal is a way of writing a fraction expressed as a base of 10. And the word decimal actually means based on 10. So decimals, they contain a decimal point. On the left side of the decimal point is a whole number, and on the right side is the fraction part. So I have a little chart here. You can see the decimal there. On the left, you have the whole number. This will be the hundredths, tens, and ones places. And then on the right of the decimal, that's the fraction portion. So that would be tenths, hundredths, thousandths, 10,000ths, and it keeps going. So for example, 0.1, that would be 1/10. 2.25, that is 2 25/100ths. Okay, so now we'll just look a little more at the number place values with decimals. So you have the decimal point. Think of that being in the middle. And then on the left side, we have the whole numbers, which are going to be numbers greater than 1. And then on the right side, we have the numbers that would be less than 1. These would be the fractions. So on the right side, we have tenths, hundredths, thousandths, 10,000ths, 100,000ths, then millionths. And it just keeps going on that way. So as it goes to the right, it gets smaller. And then for their whole numbers, as it goes to the left, it's going to get larger. So from the decimal point to the left, we have the ones, tens, hundreds, thousands, 10,000s, 100,000s, and millions places. So that just hopefully explains that a little better. So now we'll talk about naming decimals. So decimals are named by their lowest place value. And it's important to know how to name decimals when we get to some of our calculations. So 0.2, we can say 0.2, but that would be 2/10 is the way that that is said by its official name. 0.02 is 2/100ths, and 0.002 would be 2/1000ths. So when a decimal also contains a whole number, the way that you say that, you're going to read the whole number first, followed by point or and. So a common way to say it would be 3.125, but that is actually 3 125 thousandths. Okay, now we'll look at adding and subtracting decimals. So when adding and subtracting decimals, be sure that the decimal point is lined up. So for example, 0.25 plus 0.55, our decimal points are already lined up, so there's nothing we need to do but just make sure they're in a line when we add. So 5 plus 5 is 0, carry your 1. 5 plus 2 plus 1 would be 8, and then our 0 plus 0 is 0, and our decimal point just stays lined up. So the answer is 0.80. But since the 0 is the last number of the decimal, that can be removed and the value remains the same. So 0.80 is 0.8. Okay, now here's another example with subtracting a decimal. So 3.25 minus 1.2. In this case, we need to add a 0 onto the end of the decimal so that our decimal points line up. Remember, a 0 is the last number of a decimal. It can be added or removed, and the value will remain the same. So we would do 3.25 minus 1.20, and then do the math. So 5 minus 0 is 5, 2 minus 2 is 0, and then 3 minus 1 is 2. So we get 2.05. So now we'll talk about how to convert a decimal to a fraction. So this is why knowing how to read decimals is important. So for example, what is 0.1 as a fraction? So 0.1 is read as 1/10. Well, 1/10 as a fraction is 1 over 10. So 0.1 equals 1 over 10, or 1/10. And now another example. What is 0.35 as a fraction? 0.35 is read as 35/100ths. So 35/100ths as a fraction would be 35 over 100. So that would be in its fraction form, but now we need to reduce it to the simplest form. So both of these numbers are divisible by 5, so we'll do that to reduce it to the simplest form. So we'll divide our numerator and our denominator both by 5. So 35 divided by 5 is 7. 100 divided by 5 is 20. So 0.35 equals 7/20ths. Okay, so here's our chart again of our common fraction decimal equivalents. And as I said, it's not necessary to memorize this because they can be easily converted to one another, but it is helpful to know, especially if you aren't familiar with fraction and decimal equivalents. So 3/4 is 0.75, 1/2 is 0.5, 1/3 is 0.33, 1/4 is 0.25, and 1/8 is 0.125. Okay, now we're going to look at percentages. So a percentage is a number expressed as a fraction of 100, and percent actually means per 100. So percentages contain a percent sign, and just to give you an idea about what percentages mean, 100% would equal the full amount. So you could think of this as the whole pie when we were looking at fractions. 1% would be 1 part out of 100. So drug strengths are sometimes expressed as percentages and may need to be converted to fractions or decimal amounts. So that's what we're going to be focusing on with percentages. So I have our chart once again with the common fraction and decimals, and I've added the percentage equivalents on here as well. So we'll just go over those quickly again. 3/4 equals 0.75, which is 75%. 1/2 equals 0.5, which is 50%. 1/3 is 0.33, which is 33%. 1/4 is 0.25, which is 25%. And 1/8 is 0.125, which is 12.5%. So you can see the similarity between the decimal and percentage equivalents. So you can see that's easily converted. So to determine a percentage equivalent of a decimal, all you have to do is move the decimal point 2 places to the right. So for example, just 0.05, that is 5%. 0.44, we just move the decimal 2 places to the right, and that's 44%. So now we'll look at converting percentages to fractions. So first, you're going to write the percentage as a fraction by putting the number over 100. Remember, percent means per 100. And then we'll reduce the fraction to its simplest form. So for example, 5%, to write that as a fraction, will be 5 over 100. Okay, that's not in its simplest form because both numbers are divisible by 5. So we'll divide 5 by 5, and that equals 1, and then 100 divided by 5 equals 20. So 5% as a fraction would be 1/20. Now if we go the other way and convert a fraction to a percentage, what we do is multiply the fraction by 100 over 1, and then reduce the fraction to its simplest form. In this case, that's usually going to be dividing. So our example was 5/8 times 100 over 1. So 5 times 100 is 500. 8 times 1 is 8. And then if we do the math and divide 500 by 8 to get it to its simplest form, that equals 62.5%. So 5/8 as a fraction, it equals 62.5% as a percentage. Okay, now we'll look a little more at converting decimals to percentages. I briefly touched on that with our chart, but we'll just look at a little more detail here. So for converting a decimal to percentage, we're going to move the decimal point 2 places to the right. So basically what we're doing here is we're multiplying the decimal by 100. And then we'll add a percent symbol. So for example, 0.65 would be 65%. 0.2 would be 0.20. Remember, I've mentioned before that a 0 is the last number of a decimal, can be added, and the value remains the same, which in this case we need to do that to make it a percentage. So, and then we add our percent sign, so that would be 20%. 0.45, move our decimal 2 places to the right, and then add the percent sign, it's 45%. And the number 1, if we move our decimal 2 places, we can, put our zeros on there. 1.00, that's the same as 1. So 1 equals 100%. Okay, now we'll look at the other way, converting percentages to decimals. So first we're going to remove the percent symbol, and then we'll move the decimal point 2 places to the left. So here we're dividing by 100. So 99% would be 0.99. 30% would be 0.30, but then since we have the 0 on the end of the decimal, we can drop that, so it's 0.3. And 82.5% would be 0.825. Okay, now we'll look at a summary of our fractions, decimals, and percentages, just some key points here. So a fraction is a portion of a whole indicated by division of the whole into equal parts. And remember, we had our examples of the pie where you can see you divide it in 4 equal parts. One of the parts is shaded, that would be 1/4. If we have 2 of the parts shaded, that would be 2/4. So a fraction can be changed to an equivalent fraction by multiplying or dividing the numerator, remember that's the top number, and the denominator, which is the bottom number, by the same number. So for example, 2/4, it equals 1/2 when both would be divided by 2. And the line separating the portion and the whole of a fraction means to divide. Remember, per means to divide. And this is how to convert a fraction to a decimal. So for example, 1/4, that's 1 divided by 4, that equals 0.25. When the numerator equals the denominator, the fraction equals 1. So our examples, 4 over 4 equals 1, 8 over 8 equals 1, 3 over 3, that equals 1. When the numerator is greater than the denominator, the fraction is going to be greater than 1. So for example, 5 over 4 or 3 over 2, that's going to be greater than 1. To write a whole number as a fraction, put it over 1. So 4 written as a fraction would be 4 over 1. And to multiply fractions, multiply the numerators across, multiply the denominators across, and then reduce the new fraction to its simplest form. So for example, 2/3 times 1/4. If you multiply across the top and across the bottom, we get 2/12. That can be reduced if we divide the numerator and the denominator both by 2. That would equal 1/6. So a decimal, that's a way of writing a fraction expressed as a base of 10. Remember, decimal actually means based on 10. And on the left side of the decimal point is a whole number, and on the right side is the fraction. And decimals are named by their lowest place value. Remember, going from the decimal point to the right, we have tenths, hundredths, thousandths, 10,000ths. And knowing how to read decimal place value is important for converting decimals to fractions. For example, 0.1, that's 1/10, and so that's what it equals as a fraction, 1/10, 1 over 10. Remember, a percentage is a number expressed as a fraction of 100, and percent actually means per 100. And percentages can be converted to fractions and decimals. So to convert a percentage to a fraction, put the percentage over 100 and then reduce it to its simplest form. To convert a fraction to a percentage, multiply by 100 over 1 and then reduce it to its simplest form. To convert a percentage to a decimal, drop the percent symbol and move the decimal 2 places to the left. So basically you're dividing by 100. And to convert a decimal to a percentage, move the decimal 2 places to the right. So here you're multiplying by 100 and then add the percent symbol. And here's our chart that we looked at with the common fraction, decimal, and percentage equivalents. 3/4 is 0.75, which is 75%. 1/2 is 0.5, which is 50%. 1/3 is 0.33, which is 33%. 1/4 is 0.25, which is 25%. 1/8 is 0.125, which is 12.5%. And you can see an example here with our 1/4. It's drawn as the pie. We have one part out of the 4 equal parts shaded, and that would be equal to 0.25, and that equals 25%, just to give you a little more visual there. Thanks for watching. Please like and share this video with others who may find it helpful, and please subscribe to see more of my drug information videos. Thank you. Hi, my name's Amanda and I'm a pharmacist. Today I'll be talking about ratios and proportions. And if you find this video useful, please press the like button and subscribe to my channel and share it with others who may find it helpful too. Thanks, I really appreciate it. So first we'll begin with what is a ratio. A ratio is a comparison of numbers that indicates their sizes in relation to each other. And there are 2 ways to write a ratio, as a fraction or with a colon. And I'll just give you an example just to show you more what I mean here. If we have 5 grams of dextrose in 100 milliliters of water, this is known as D5W, the ratio of dextrose to water could be expressed as 5 over 100 as a fraction, and you would say that 5 per 100, or 5 with a colon 100, and you would say that 5 to 100. And most ratios in pharmacy are stated as a fraction. So now we'll look at proportions. So what is a proportion? Proportions express the relationship between 2 equal ratios. You can think of these as equivalent fractions. And I'll just give you an example to show you what I mean here. If there are 5 grams of dextrose in 100 milliliters of water, remember this is D5W, there will be 10 grams of dextrose in 200 milliliters of water. So you can see both the dextrose and the water double. And so written as a proportion, where you can think of this as equivalent fractions or equal ratios, 5 over 100 equals 10 over 200. Now we'll talk about ratio and proportion calculations. Many types of pharmacy calculations can be solved using ratio and proportion calculations. This includes conversions, days supply, concentrations, just to name a few, and there are others as well. Proportions are useful because if 3 out of the 4 numbers are known, the 4th number can be calculated. An unknown number in math is called a variable. It's represented by a letter. X is commonly used. And if you know anything about algebra, you'll be familiar with this, but if not, don't worry, you'll still understand how to do this math. The basic steps for solving a proportion calculation, you set up equivalent fractions, cross multiply, then divide. And we'll go through some examples here. So example number 1. How many grams of dextrose are in 25 milliliters of a solution containing 5 grams of dextrose in 100 milliliters of water? So first we'll set up equivalent ratios. What we know is 5 grams of dextrose, so 5 grams over 100 milliliters, and we'll set that equal to X grams. Remember, X is a variable representing the number we're looking for. Over 25 milliliters. So we have 3 of the numbers. We're going to solve for the 4th number to get the answer. So we set up the equivalent ratios. Now we're going to cross multiply. This just means to multiply in an X pattern when you have equivalent ratios set up here. So we can do 5 times 25 equals 100 times X. And if we just simplify that, we get 125 equals 100x. And then we just have to divide to get our answer. Divide to solve for x. So we have 125 divided by 100. That will give us x, what our answer is we're looking for. And that is, if we do the math, it's 1.25 grams. Okay, now another example, example number 2. How many grams of sodium chloride are in 50 milliliters of a solution containing 9 grams of sodium chloride in 1 liter of water? And just a note here, 9 grams per 1 liter of sodium chloride solution. This is a product called normal saline. Just something else to throw in there for you to know. So first, our steps for our ratio and proportion calculations. Number 1, we set up equivalent ratios. So what we know is we know 9 grams of sodium chloride in 1 liter of water, which if you'll remember from our conversion equivalents, we know that 1 liter equals 1,000 milliliters. An important point here to know is that the units must match. So we have grams and milliliters. We want to have grams and milliliters in both of the ratios. So 9 grams per 1,000 milliliters equals X grams, or that's our unknown, over 50 milliliters. So next we'll cross multiply. 9 times 50 equals 1,000 times X. We simplify that. That's 450 equals 1,000X. Now we'll divide to solve for X. So 450 divided by 1,000 gives us our answer, which is 0.45 grams. So just a summary here to review. A ratio is a comparison of numbers that indicates their sizes in relation to each other. You can think of this usually in pharmacy as a fraction. It's going to be set up. Proportions express the relationship between 2 equal ratios. So you can think of proportions as just equivalent fractions. Proportions are useful because if 3 out of the 4 numbers are known, the 4th number can be calculated. And the basic steps for solving a proportion calculation: number 1, we're going to set up equivalent fractions. 2, cross multiply. And 3, divide to get our answer. Thanks for watching. Please like and share this video with others who may find it helpful, and please subscribe to see more of my drug information videos. Thank you. Hi, my name's Amanda and I'm a pharmacist. Today I'll be talking about a type of pharmacy calculation called conversions. And if you find this video useful, please press the like button and subscribe to my channel and share it with others who may find it helpful too. Thanks, I really appreciate it. So we'll begin with what are conversions. Conversions are the changing from one unit of measure to a different unit of measure. For example, going from ounces to milliliters or grams to milligrams. The most common conversions in pharmacy are for measures of weight and volume, and sometimes length, so we'll cover those as well. The key to conversion calculations is memorization of the commonly used conversion equivalents. Now we'll look at the different systems of measurement. There's the U.S. customary system and the metric system. These are two systems of measurement that are commonly seen. The United States customary system is derived from English units with no pattern of relationship between one another. This is the one most of us are familiar with. 1 yard equals 3 feet equals 36 inches. There's not really a pattern of numbers for equivalents. The metric system, however, is based on multiples and fractions of 10, which make converting between larger and smaller units easy. So both systems are used in the medical field, and many of the common conversions are for changing measurements from one system to the other. Now we'll look more at the metric system. It centers on a base unit that increases or decreases by multiples and fractions of 10. And there's a prefix that indicates its relationship to the base unit. And that's the main thing to look at with this chart, is to know the relationship between the prefix and the base units. So if you look in the middle of the chart where it says base unit, the base units are gram, liter, and meter. And moving up the chart, first we see the prefix deci. So a decigram would be 1/10 of a gram. Then a centigram would be 1/100th of a gram. A milligram would be 1/1000th of a gram, and a microgram would be 1/10,000th of a gram. And then if we come back to the base unit, and then going the other way, first we have decagram. So 10 grams would equal 1 decagram. Hectogram, 100 grams would equal 1 hectogram. And kilogram, 1,000 grams would equal 1 kilogram. And I've put in bold here the ones that are the most commonly seen in pharmacy. So microgram, which is abbreviated with the lowercase Greek letter mu, or MC with a G, be microgram. Milligram, which is mg, or milliliter, ml. Centimeter, cm, and then kilogram, or kg. Now we'll look at the weight conversions. Weight conversions are used to determine solid medication dosages and quantities, and for waste-based dosage calculations. So this chart are the common weight conversion equivalents that should be committed to memory. With gram, 1 gram equals 1,000 milligrams. Milligram, 1 milligram equals 1,000 micrograms. Kilogram, 1 kilogram equals 1,000 grams, and that also equals 2.2 pounds. Grain, which is GR, 1 grain equals 64.8 milligrams. And I just put a note here, GR is the abbreviation for grain. That does not equal gram. The G or GM is gram, so be sure you know the difference between those. Pound, which is LB, 1 pound equals 454 grams. Now we'll look at the volume conversions. The volume conversions are used to determine liquid medication quantities and doses. And here this chart shows the common volume conversion equivalents in pharmacy. A teaspoon, TSP, 1 teaspoon equals 5 milliliters. A tablespoon, which is TBSP, 1 tablespoon equals 15 milliliters, which also equals 3 teaspoons. Liter, which is L, 1 liter equals 1,000 milliliters. Milliliter, or ml, 1 milliliter equals 20 drops, and if you remember, drops is often abbreviated GTTS, and that also equals 1 cc, which stands for cubic centimeter. For ounce, it's OZ, or it's also seen as a fluid ounce. 1 ounce equals 30 milliliters. And gallon, or GAL, 1 gallon equals 4 quarts, which equals 8 pints. And a pint, which is PT, 1 pint equals 473 milliliters. And the last two on there, I didn't bold those because those aren't as common, but they still are ones you need to know. Now we'll look at the length conversions. As I said, length conversions aren't used much in pharmacy, but they're good to know for tests. So some common length conversion equivalents, inch, which is abbreviated IN, 1 inch equals 2.54 centimeters. Meter, which is M, 1 meter equals 100 centimeters. And feet, which is FT, 1 foot equals 12 inches. And now we'll look at how we solve conversion calculations, and there are two methods we'll look at today. And I just thought the best way to explain this is just to have an example of something that we need to convert, and then we'll look at how to solve it. So the example here is how many ounces are in 300 milliliters. So what we know, remember I said we need to memorize these conversions that were on the tables, 1 ounce equals 30 milliliters. So knowing that, with method 1, what we'll do is set up fractions that cancel like units of measurement, and then we'll multiply the fractions to get the answer. So there's 1 ounce per 30 milliliters. And you can just think of, per means to divide, so you can set that as a fraction. 1 ounce over 30 milliliters. And then that will be times 300 milliliters over 1. Remember, to make a whole number into a fraction, you just put it over 1. And then for like units to cancel, we have to have 1 on the top, 1 on the bottom. So you see we have a milliliter on the top in the second fraction, and there's a milliliter on the bottom from the first fraction. So we can just mark those out, those cancel, and then that leaves us with ounces, which is what we are looking for, how many ounces. And so if we just do the math here, we have 300 ounces divided by 30, because our milliliters were canceled out, so all we're left with is ounces, and that equals 10 ounces. So just something to remember with this method is the unit that you're looking for must be on the top. After your units cancel, you want to make sure that the one that you're looking for is left on the top, so that will give you the correct answer. And now method number 2, the same problem. How many ounces are in 300 milliliters? As I said, what we know from our memorization, 1 ounce equals 30 milliliters. So with this method too, we're going to set up equivalent fractions, cross multiply, and then divide. So there's 1 ounce per 30 milliliters, and we're going to see if that is equal to X ounces, where X here is a variable representing the answer we're looking for, per 300 milliliters. So we've set up, this is sort of an algebra way to do it. And the first thing we'll do is cross multiply. So we have 1 times 300, and that gives us 300. And then we'll divide by the other side to solve for X. So 300 divided by 30 equals 10 ounces. And now we'll just look at a summary and kind of a review of the conversions video. Conversions are the changing of one unit of measure to a different unit of measure, and memorization is key. You have to know the equivalents to be able to even begin a conversion calculation. And I'll just review the common conversion equivalents once more here. 1 gram equals 1,000 milligrams. 1 milligram equals 1,000 micrograms. 1 kilogram equals 1,000 grams, which also equals 2.2 pounds. 1 grain, remember this is GR is the abbreviation, is 64.8 milligrams. 1 pound equals 454 grams. 1 inch equals 2.54 centimeters. 1 meter equals 100 centimeters. 1 teaspoon equals 5 milliliters. 1 tablespoon equals 15 milliliters, which also equals 3 teaspoons. 1 liter equals 1,000 milliliters. 1 milliliter equals 20 drops. Remember, drops is abbreviated GTTS sometimes, which also equals 1 cc, which is a cubic centimeter. 1 ounce equals 30 milliliters. 1 gallon equals 4 quarts, which equals 8 pints. 1 pint is equal to 473 milliliters. Thanks for watching. Please like and share this video with others who may find it helpful, and please subscribe to see more of my drug information videos. Thanks. Hi, my name's Amanda and I'm a pharmacist. Today I'll be talking about days supply calculations. And if you find this video useful, please press the like button and subscribe to my channel and share it with others who may find it helpful too. Thanks, I really appreciate it. So first we'll just have an overview of days supply. Days supply is basically just how many days the quantity of a prescribed medication will last. Like for example, 7 days, 30 days, etc. And this video will cover days supply calculations for solid dosage forms. This includes tablets and capsules, oral liquids such as suspensions and solutions, inhalers and nasal sprays, eye and ear drops, and injectables. We'll be focusing on insulin. So first we'll look at some basic information about the days supply calculations. Days supply for a prescription may be given or it may need to be calculated. If the days supply is given, the amount of medication to dispense must be calculated. This is done by taking the amount of medication used in one day and multiplying it by the number of days to use the medication. So for example, if the prescription is for taking 2 tablets per day and is for 30 days, that would be 2 times 30, which would be to dispense 60 tablets. If the days supply needs to be calculated, you take the total amount of the medication dispensed and divide that by the amount of medication used in one day. And in order for this to work, these have to be in the same units. And this is where the conversion calculations may be needed. So for example, if you have 60 tablets, is going to be the total amount of medication dispensed. And the amount of medication used in one day was 2 tablets, you would just divide 60 by 2, and that would give you 30 days. So let's look more closely at the different types of prescriptions for the days supply. First, we'll start with the solid dosage forms. This includes tablets, capsules, suppositories, or anything that's in a unit dose. And I thought the best way to do this is to actually give prescription examples with a question. So this first one is for metformin 500 milligram tablets, 1 BID, that's 1 twice a day, dispense a 1-month supply, refill times 3. So how many tablets should be dispensed for this prescription? So we'll take our number of tablets used in one day, multiply it by the number of days. That will give us the answer. So 1 BID, that's twice a day, so that would be a total of 2 tablets in a day, and times 1 month. 1 month, a good number to use for that is just 30 days because that's a good round number. So 2 times 30 will be 60 tablets. We'll look at another example of solid dosage form days supply. This one is amoxicillin 500 milligram capsules, 1 TID UAT. Means 1 3 times a day until all are taken. Number 21 to be dispensed and no refills. So here we have the quantity and we're going to need to calculate the day's supply. So what is the day's supply for this prescription? So we're going to take the total amount of medication dispensed divided by the amount of medication used in one day, and that'll give us the answer. So the total is 21 capsules to dispense and 1 TID. That's 1 3 times a day, so that would be a total of 3 capsules in a day. So 21 divided by 3 gives us 7, so it's a 7-day supply. Now we'll look at the oral liquids days supply. Oral liquids, this includes suspensions, solutions, and syrups. And this may involve the volume conversion calculations, so I thought this will be a good place to review those. The common volume conversion equivalents include 1 teaspoon equals 5 milliliters. 1 tablespoon equals 15 milliliters, which equals 3 teaspoons. 1 milliliter equals 20 drops, which equals 1 cc. 1 ounce equals 30 milliliters, and 1 liter equals 1,000 milliliters. So our first prescription we have here is for amoxicillin 250 milligram per 5 ml suspension. And the directions are 1 teaspoon BID times 10D. That's 1 teaspoonful twice a day for 10 days. Dispense quantity sufficient, QS, and with no refills. So how much amoxicillin suspension should be dispensed for this prescription? From our conversion equivalents, we know that 1 teaspoon equals 5 milliliters. So this is for 5 milliliters, 1 teaspoon, BID, which is twice a day. So that would give us a total of 10 milliliters per day. So now we're going to take the amount used in one day and multiply it by the number of days. So that's 10 milliliters times 10, those 10 days, gives us a total of 100 milliliters is how much we need to dispense. Okay, we'll look at one more example now for the oral liquids day supply. So we have Robitussin AC cough syrup, 1 teaspoon PO Q4 to 6H PRN cough. That's 1 teaspoonful by mouth every 4 to 6 hours as needed for cough. Dispense 4 ounces with no refills. So what is the day's supply for this prescription? Okay, from our conversion equivalents, we know that 1 teaspoon equals 5 milliliters. So that's going to be 5 milliliters 6 times a day. We get the 6 times a day because the maximum that could be taken would be, it could be taken every 4 hours. So there are 24 hours in a day, so we would divide 24 by 4, which gives us 6 times a day. So 5 milliliters times 6 times a day, 5 times 6 gives us 30 milliliters that could be taken in one day. And now we need to convert our amount dispensed also to milliliters, because remember this has to be, they have to be in the same units. So we have 30 milliliters in 1 ounce, and we're doing 4 ounces here. So it'd be 30 milliliters over 1 ounce times 4 ounces over 1, and our ounces cancel, if you remember from our conversion calculations, and so we have 30 times 4 gives us 120 milliliters. So now we'll just take our total amount of medication dispensed and divide it by the amount of medication used in one day. So 120 divided by 30 gives us a 4-day supply. Now we'll look at the inhalers and nasal sprays day supply. So inhalers and nasal sprays have a specified number of metered doses per container. The number of doses per inhaler or bottle of nasal spray is product specific and can be found by reading the label on the product. The number of doses may be on the product label as metered inhalations. This is usually for inhalers, or metered sprays. This will be for the nasal sprays, or it may just say metered doses. We'll look at our first example here. Albuterol inhaler, 90 micrograms. 1 to 2 puffs, Q6H, PRN wheezing. Dispense 1 inhaler, refill times 3. So that's, we know from our albuterol package that it comes, the 1 inhaler has 200 metered doses. So if we calculate the maximum amount of medication for 1 day, the max would be 2 puffs, and it'd be 4 times a day, Q6 hours. You have 24 hours in a day. Divided by 6 hours will give us 4 times a day it could be used. So 2 times 4 would give us 8, a maximum of 8 doses per day. And we know from our package that it's 200 metered doses. So now we'll just do our calculation of the total amount of medication dispensed divided by the amount of medication used in 1 day. So we have 200 divided by 8, and that gives us a 25-day supply. And one more example now with a nasal spray. We have Flonase nasal spray, 2 sprays QD into each nostril. Dispense 1 bottle, refill times 2. So QD is once a day, so 2 sprays once a day. And we know from our Flonase bottle, it has 120 metered sprays in it. So the amount of medication in 1 day, 2 sprays into each nostril, so you have 2 nostrils, so it'd be 2 times 2. That will be 4, and it's just once a day. So it's a total of 4 sprays a day. So now we're going to take the total amount of medication dispensed, divide it by the amount of medication used in 1 day. So 1 bottle, we know from the package, it has 120 sprays. We divide that by 4 sprays a day, and that gives us a total of 30-day supply. Okay, now we'll look at the eye and eardrops day supply. Day supply calculations for eye and ear drops, they typically require a conversion calculation first. And it's just the 1 ml or milliliter equals 20 drops. Remember, drops can be abbreviated GTTS. So eye and ear drops come in different size bottles. For example, we can have a 2.5 milliliter, 5 milliliter, or 10 milliliter bottle. It's the same product, but they just come in different sizes. And sometimes a calculation is required to determine the correct bottle size to dispense to the patient with eye and ear drops. So we'll look at that, an example of that as well. So our first eye and ear drop example, we have a prescription for Xalatan, 0.005% ophthalmic solution. And the directions are 1 GTT OU QPM. That's 1 drop into each eye every evening. Dispense 2.5 milliliters with no refills. So the question here is, what is the day's supply for this prescription? So the directions are 1 drop into each eye every evening. So that's just 1 drop, and you have 2 eyes, so that would be 2 drops, and once a day, so it'd be 2 times 1. That gives us a total of 2 drops per day. And we know from our conversion equivalent that 1 milliliter equals 20 drops. So we simply take 2.5 milliliters and multiply it by 20 to find out how many drops are in the 2.5 milliliter package. That gives us a total of 50 drops. So now we're going to take our total amount of medication dispensed, divide it by the amount of medication used in one day. So 50 drops is how much is to be dispensed, divided by 2 drops. 50 divided by 2 gives us a 25-day supply. And one more example in the eye and ear drops. We have prednisolone 1% ophthalmic suspension, 2 GTTS OS TID times 7D. So that's 2 drops into the left eye 3 times a day times 7 days. Dispense 1 bottle with no refills. So what size bottle should be dispensed for this prescription? And 2.5, 5, or 10 ml sizes are available. So those are our choices. So this is for 2 drops 3 times a day, just into one eye. So it would be 2 times 3. That gives us a total of 6 drops per day. And then we're going to do that for 7 days. So 6 drops a day times 7 days. 6 times 7 is 42 drops total. Now we know from our conversion equivalents that 20 drops equals 1 milliliter. So what we need to find out now is how many milliliters does 42 drops equal. So we simply set up our conversion calculation, 1 ml per 20 drops times 42 drops over 1. Our drops cancel out, we're left with milliliters. And so we have 42 divided by 20. That gives us 2.1 milliliters. So the size that would be closest to that would be the 2.5 milliliter bottle. Now we'll look at the injectables day supply. We're really going to focus on insulin here because that's the most common day supply calculation for injectables. The doses for insulin are specified in number of units to inject. And something to know about injectables is they may have a short expiration date after opening, and this must be taken into consideration when determining the day supply for these products. Insulins expire 28 days after opening. That's something you'll want to know. The number of units per milliliter in a vial of insulin also depends on the specific insulin product. A little more details about that. U100 insulin is the most common concentration, but there are others. And with U100 insulin, that equals 100 units per milliliter. And I've listed here some common U100 insulin products: Novolog, or insulin aspart, Humalog, which is insulin Lispro, Lantus or Basaglar, which is insulin Glargine, Levemir, which is insulin Detamir, and Tresiba, which is insulin Degludec. So the common insulins that are in the top 200 drugs are actually U100 insulins, but I have a note here that the Tresiba and the Humalog are also available in U200. So it's just something to watch for. The concentration, which is the units per ml of insulin, is on the package. If there are ever any questions, you can just look at the package and see what the units per ml is on that. And something that's helpful to know, a 10 milliliter vial of U100 insulin equals 1,000 units. So that's something you'll want to memorize. So we'll look at a couple examples here. Lantus, 100 units per milliliter. 5U SQ QHS. That's 5 units subcutaneously, which is under the skin, every night at bedtime. Dispense a 10 milliliter vial, refill times 3. So what is the day's supply for this prescription? So the amount for one day is 5 units, because it's just 5 units once at bedtime. And then a 10 ml vial of U100 insulin, that's what we're dispensing here, equals 1,000 units. That's that little helpful thing I said to memorize. So we'll take the total amount of medication dispensed, divide it by the amount of medication used in one day. So we have 1,000 units divided by 5 units so that equals a 200-day supply. But insulin expires 28 days after opening, so the day supply for this prescription would be 28 days. One more example here for insulin. We have Humalog Quick Pen U100, 20U SQ TID AC. That's 20 units subcutaneously under the skin 3 times a day before meals. Dispense 5 3-milliliter pens and refill times 2. So what is the day supply for this prescription? 20 units 3 times a day would be a total of 60 units for 1 day, 20 times 3. And then to find out how much is in the 5 pens, we have 5 3-milliliter pens, so that would be a total of 15 milliliters. So we know this is U100 insulin, so that means 100 units per 1 ml. And we'll multiply that by 15 milliliters. Our milliliters cancel out, we're left with our units on the top. So that equals 100 times 15 equals 1,500 units will be dispensed. So now we're going to take our total amount of medication dispensed and divide it by the amount of medication used in 1 day. So we have 1,500 divided by 60, and that gives us a 25-day supply. And we know insulin is good for 28 days, so that day supply, we can leave it as is. So now we'll just look at a little summary of our day supply calculations. Day supply is how many days the quantity of prescribed medication will last. If day supply is given, the amount of medication to dispense has to be calculated. And this is done by taking the amount of medication used in 1 day and multiplying it by the number of days to use the medication. And if day supply needs to be calculated, we take the total amount of medication dispensed and divide it by the amount of medication used in 1 day. And remember, these must be in the same units for this to work. And conversion calculations may be needed to obtain the same units before the day supply can be calculated. So thanks for watching. Please like and share this video with others who may find it helpful, and please subscribe to see more of my drug information videos. Thank you. Hi, my name's Amanda and I'm a pharmacist. Today I'll be talking about a type of pharmacy calculation called concentrations. And if you find this video useful, please press the like button, subscribe to my channel, and share it with others who may find it helpful too. Thanks, I really appreciate it. So we'll start with a definition. So what are concentrations? Concentrations are the strengths of liquid and topical products. And more specifically, a concentration is the amount of active ingredient per the total weight or volume of the product. So a formula for determining concentration is concentration equals the amount of active ingredient per, which means divided by, the total weight or volume of the product. And there are a few different ways that a product's concentration can be expressed. It can be expressed as a drug strength. This would be something like amoxicillin suspension, 250 milligram per 5 milliliters. That's the concentration. As a percentage, this will be something like 5% dextrose IV solution. 5% is the concentration of that solution. Or it can also be expressed as a ratio. This will be something like epinephrine 1 to 1,000 injection. The drug strength and percentage are the more common ways that a product's concentration is generally expressed. Ratio is not as common, but we're going to talk specifically about each of these now. So first we'll look at concentration as a drug strength. Concentration as a drug strength is the amount of active drug per a given amount of drug product. And remember, we're talking here about liquid and topical products. So for drug strengths, there are many different units of measure. It's generally something per something. So it can be milligrams per milliliters, micrograms per milliliters, units per gram, grams per milliliters, and so on. There are many different units of measure. Here are some different types of drug strength concentrations. There are amount of drug per dosage unit. An example of this will be something like albuterol nebulizer solution unit doses. These come in 2.5 milligrams per 3 milliliter for each vial. There's also amount of drug per quantity of liquid. An example of this would be amoxicillin suspension, 250 milligrams per 5 milliliters. Or there are amount of drug per quantity of a topical product. this will be something like nystatin cream, 100,000 units per gram. Now we'll look at some drug strength concentrations questions. Question number 1. How many milligrams of prednisolone are in 100 milliliters of prednisolone 15 milligram per 5 ml solution? The way we're going to solve this is we're going to set up equivalent fractions, cross multiply, and then divide. And if you've seen any of my other pharmacy calculation videos, you know that this is a very common method for solving pharmacy math problems. So we know the concentration of our prednisolone solution is 15 milligrams per 5 milliliters, so that'll be our first fraction, 15 milligrams per 5 mLs, equals X milligrams, that's what we're looking for, is how many milligrams per 100 milliliters. So the other fraction is X milligrams per 100 milliliters. And X here is the variable representing the answer we're looking for. Next, we're going to cross multiply. So 15 milligrams times 100 milliliters equals 1500. Then we're going to divide to solve for X. So 1500 divided by 5 equals 300. So that's 300 milligrams are in 100 milliliters of prednisolone, 15 milligram per 5 ml solution. And also note here that our numerators, which is the top number of the fractions, they have to be the same units, and the denominators have to be the same units, which are the bottom numbers of the fractions. So, and it is that way, the 15 milligrams, and then we have X milligrams, and we have 5 milliliters and 100 milliliters. So that always has to be set up for these equivalent fraction, this equivalent fraction method to work. Okay, drug strength concentrations question number 2. How many milligrams of amoxicillin are in 50 milliliters of amoxicillin 400 milligram per 5 ml suspension? We're going to solve this one the same way. We're going to set up equivalent fractions, cross multiply, and then divide. So we have our concentration of the amoxicillin suspension is 400 milligrams per 5 mLs. That'll be our first fraction. We'll set that equal to X milligrams, that's what we're looking for, per 50 milliliters. We'll cross multiply, so 400 times 50 equals 20,000, and then we'll divide to solve for X. So 20,000 divided by 5 equals 4,000. So that's our answer. There are 4,000 milligrams of amoxicillin in 50 milliliters of an amoxicillin 400 per 5 suspension. Now we'll look at drug strength concentrations question number 3. If there are 800 milligrams of acetaminophen in 25 milliliters of Tylenol suspension, how many milligrams of acetaminophen are in each teaspoonful? So we're going to solve this one the same way. We're going to set up equivalent fractions, cross multiply, then divide. So we know the concentration, 800 milligrams of acetaminophen per 25 milliliters of Tylenol. So our first fraction is 800 milligrams per 25 milliliters. And we'll set this equal to X milligrams, that's what we're solving for, is the milligrams, per 5 milliliters. It says in each teaspoonful, but 1 teaspoonful equals 5 milliliters. Remember, I said our units have to match, so we have milligrams and milligrams on the top of the fractions, milliliters and milliliters on the bottom of the fractions. So next we'll cross multiply, so 800 times 5 equals 4,000. Then we'll divide to solve for X. 4,000 divided by 25 equals 160 milligrams. So in each teaspoonful of Tylenol suspension, there's 160 milligrams of acetaminophen. Now we'll look at concentration as a percentage. So percent means per 100, or you can think of it as divided by 100. And there are 3 formulas for concentrations as percentages. There's weight per weight, or sometimes you may hear this as weight in weight. This means grams of drug per 100 grams of product, so those are both weight units of measure. There's weight per volume, or weight in volume, and I have a star here beside it because it is the most common one you'll probably see. And this means grams of drug per 100 milliliters of product, so it's a weight unit on the top and a volume unit on the bottom. And then there's volume per volume, or volume in volume. And this is milliliters of drug per 100 milliliters of product. So both are milliliters are volume units of measure. So you can think of the formula for concentration as a percentage as grams or milliliters of drug per 100 grams or 100 milliliters of the total product. And I'll give you an example here. If we have 5% dextrose solution, this means there are 5 grams of dextrose per 100 milliliters of solution. So 5 grams per 100 mLs. That is equal, you can say 5 per 100, which remember percent means per 100, so 5 per 100 equals 5%. And here are some common IV product abbreviations and concentrations. You'll want to memorize these and what they mean, because these are common abbreviations in pharmacy, especially in a hospital setting. So there's D5W, this means dextrose 5%. And this means that there are 5 grams of dextrose in 100 milliliters of sterile water. NS, that stands for normal saline, and that is 0.9% NaCl, which is sodium chloride. And this means a concentration of 0.9 grams of sodium chloride in 100 milliliters of sterile water. Then there's half NS, which is half normal saline. This is 0.45% NaCl, which is sodium chloride. And the concentration of this would be 0.45 grams of sodium chloride in 100 milliliters of sterile water. So now we'll look at some percentage concentration questions. We'll start with question number 1. How many grams of dextrose are in 250 mLs of D5W? So first, we have an abbreviation here of our product, so we need to determine the concentration of the product. D5W, that means dextrose 5%, so that means 5 grams of dextrose per 100 milliliters. So next we're going to set up equivalent fractions, cross multiply, and then divide. So our first fraction is going to be our 5 grams per 100 milliliters, and we'll set this equal to X grams, that's what we're solving for, is for the grams, per 250 milliliters. Next we'll cross multiply, so we'll take 5 times 250, that equals 1,250, and then we'll divide to solve for X. So then we'll divide by 100, and that equals 12.5 grams. So there are 12.5 grams of dextrose and 250 mLs of D5W. Now we'll look at percentage concentration question number 2. How many grams of NaCl are in 1 liter of NS? So this again is an abbreviation for a product. NS is normal saline, so we have to determine the concentration. So NS is normal saline, and that's equal to 0.9% NaCl. And that means 0.9 grams of NaCl per 100 milliliters. So now we can set up equivalent fractions, cross multiply, then divide. So we have 0.9 grams per 100 milliliters. That's the concentration of the normal saline. We're going to set that equal to X grams. That's what we're looking for, how many grams per 1,000 milliliters. Notice in the question it's 1 liter is what we're looking for, but remember our units have to match. The numerator units and the denominator units of the fractions have to match. So since we have milliliters in our first fraction, it has to be milliliters in our second fraction. And if you've memorized your conversions, you know that 1 liter equals 1,000 milliliters. So now that we have that set up, we'll cross multiply. So we have 0.9 grams times, or 0.9 times 1,000, and that equals 900. Then we will divide to solve for X. So 900 divided by 100 equals 9 grams. So there are 9 grams of NaCl in 1 liter of normal saline. Okay, we'll look at one more percentage concentration question. Question number 3. How many milligrams of hydrocortisone are in 1 gram of 2.5% hydrocortisone cream? So this one we're going to set up equivalent fractions, cross multiply, then divide. We don't have to figure out our percentage because it's already given. And we just need to know what that percentage means. So 2.5%, that means 2.5 grams per 100 grams. So that's going to be our first fraction, and we're going to set that equal to x over 1 gram because we're looking for how much in 1 gram. And our unit for x is going to be grams. Remember, our fractions units have to match. What's on the top of one fraction has to be what's on the top of the other fraction, and the bottom units have to match as well. So first we're going to solve for x in grams, and then we'll convert it to milligrams for our final answer here. So we have our equivalent fractions set up, so now we'll cross multiply. 2.5 times 1, that equals 2.5. Then now we'll divide to solve for x. So 2.5 divided by 100 equals 0.025 grams. Now we need to convert to our correct units. We need to convert from grams to milligrams. And to do this, there are 100 milligrams per 1 gram. And we're going to multiply that by 0.025 grams over 1. Our grams cancel out because there's a gram on the top, a gram on the bottom, and we're left with milligrams for the top unit. So that's what we want. We want this in milligrams. So now we'll just do the math and multiply 1,000 times 0.025, and that gives us 25 milligrams. So there are 25 milligrams of hydrocortisone in 1 gram of the 2.5% hydrocortisone cream. Now we'll look at concentration as a ratio. Ratio strength describes a drug concentration in terms of a ratio. You can think of a ratio as a fraction with a colon. So like 1 to 200 would equal like 1 per 200. Ratio strength is generally 1 to something. So for example, 1 to 1,000, 1 to 2,000, 1 to 10,000. The formula for ratio strength to concentration is grams to milliliters. So for example, a ratio strength of 1 to 1,000 would mean there's 1 gram in 1,000 milliliters of solution. Ratio strengths are used to express concentrations of weak solutions when the percentage strength is very low. For example, a ratio strength of 1 to 10,000 is equal to 0.01%. So you can see how it can be a more convenient way of expressing a low concentration. However, ratio strengths are not very common anymore because they've been linked to medication errors. In 2016, the FDA required removal of ratio strengths from labels of single ingredient products. And you will still see those on multi-ingredient products. And this was to help prevent medication errors. Labels were changed to express drug strength instead of a ratio. So one of those products that was affected was epinephrine injection. So it comes in a 1 to 1,000 strength, and it also comes in a 1 to 10,000 strength. So you can see how those are very similar. Just 1 0 is all that makes a difference, and they're very different concentrations, but because they look similar, that can increase the risk for medication errors. So these aren't as common, the ratio strengths, but they still are used somewhat. So we'll look at a couple questions with those. Ratio concentrations, question number 1. How many milligrams of epinephrine are in 10 milliliters of epinephrine 1 to 200 solution? So we're going to do these very similar to the other concentration problems. We'll set up equivalent fractions, cross multiply, and then divide. So a ratio concentration of 1 to 200 would be equal to 1 gram per 200 milliliters. So that's our first fraction, 1 gram per 200 milliliters. And this will set equal to x grams per 10 milliliters. Remember, we are solving for milligrams here, but we have to set it for grams because our top numbers of the fractions have to match. Our top units of the fractions have to match, and our bottom units of the fractions have to match. So we'll first solve for the x in grams, and then we'll convert it to milligrams. So now that our equivalent fractions are set up, we'll cross multiply. 1 times 10 equals 10. Then we'll divide to solve for x. 10 divided by 200 equals 0.05 grams. Now we'll convert to the correct unit. We're going from grams to milligrams. So we'll do 1,000 milligrams per 1 gram. That's how many milligrams are in a gram. Times 0.05 grams per over 1. Just to put it over something, because the number over 1 is equal to itself. So now our grams cancel out because we have a gram on the top of a fraction and one on the bottom, so those cancel. We're left with the unit of milligrams. Now we'll do the math and multiply 1,000 times 0.05, and that equals 50 milligrams. So there are 50 milligrams of epinephrine in 10 milliliters of an epinephrine 1 to 200 solution. You can also do the conversions of grams to milligrams by moving the decimal place. And if you know how to do that, that's great. But I like to set it up this way just so that you're sure that you're getting going the correct way, moving the decimal place. And that this is a good way to check because the unit that you're looking for is always going to be left on top and your other units will cancel out. Okay, ratio concentrations question number 2. If an epinephrine product has a strength of 1 milligram per milliliter, what is the concentration expressed as a ratio? So first we need to convert to correct units for equivalent fractions. Remember the ratio units are grams to milliliters. So first we'll convert milligrams to grams. Remember 1 gram equals 1,000 milligrams. So we have 1 gram per 1,000 milligrams times 1 milligram over 1. And that is, our milligrams cancel because there's one on the top, one on the bottom. We're left with the unit of grams, and that is equal to 0.01 grams. So now we'll set up our equivalent fractions, cross multiply, and then divide. So our first equivalent fraction would be 0.01 grams per 1 milliliter. That's what we took from our ratio. Remember, it's grams per milliliter, so that's our ratio. And we'll set that equal to 1 gram per X milliliters. This one's a little different. We know that a ratio concentration is 1 to something. So our 1 gram is at the top and we're solving for the X milliliters on the bottom. So we'll cross multiply and divide to get our answer. 1 times 1 equals 1. Then we'll divide by 0.001, and that gives us 1,000 milliliters. But that's not our answer because we're looking for a ratio. So our answer is, if an epinephrine product has a strength of 1 milligram per milliliter, what's the concentration expressed as a ratio? It's 1 to 1,000. So it's the entire second fraction, 1 gram to 1,000 milliliters, or 1 to 1,000. Okay, now we'll just look at a summary and some key points to remember about concentrations. Concentrations are the strengths of liquids and topical products. Remember, as a formula, this would be the amount of drug per the total weight or volume of the product. There are drug strength concentrations. Remember, these come in many units of measure: milligrams per milliliter, grams per milliliter, micrograms per milliliter, units per gram, many different units of measure. Percentage concentrations, percent means per 100, and the units for a percentage concentration are grams or milliliters per 100 grams or 100 milliliters. So we have to be in grams and milliliters with percentages. And then there are ratio concentrations. Ratio generally means 1 to something, and the units for ratio concentrations are grams to milliliters. And the steps for solving concentration questions. First, we're going to set up equivalent fractions with correct units. Remember, our top numbers of the fractions have to match units, and the bottom numbers of the fractions have to match units. We're going to cross multiply and then divide to solve for X. And then we'll convert our answer to the correct unit, what was asked in the question, if needed. That isn't always necessary. Thanks for watching. Please like and share this video with others who may find it helpful, and please subscribe to see more of my drug information videos. Thank you. Hi, my name's Amanda and I'm a pharmacist. Today I'm going to be talking about a type of pharmacy calculation called dilutions. And if you find this video useful, please press the like button, subscribe to my channel, and share it with others who may find it helpful too. Thanks, I really appreciate it. So first we'll begin with a definition. What are dilutions? Dilutions are drug products with increased volume, which causes a decrease in concentration. When a product is diluted, the quantity of active ingredient actually remains the same, but the concentration of the product decreases because of the increased volume. So I have an illustration here. You can see the small circle with the 5 dark blue circles inside it. We'll say that's 5 grams per 100 milliliters is its concentration, which is 5%. So dilution, which is adding more volume, we'll say we add 100 milliliters to this. That's going to give us a concentration now of 5 grams per 200 milliliters, which would be 2.5%. So you can see our drug amount, the active ingredient, actually remains the same. In both cases it's 5 grams, but the amount of volume is what has increased. So that's what dilutions are about. There are a couple different types of dilutions we're going to talk about. There are liquid dilutions. These are weight per volume, usually in the units of gram per milliliter. And these are solutions. Solid dilutions, these are weight per weight. Generally you see these in gram per gram. And this includes creams and ointments. And pharmacy dilution problems typically involve determining how to make a weaker product from a more concentrated stock product. And this is our formula for solving dilution problems. Q1 times C1 equals Q2 times C2. And you'll want to memorize this. Q1 is quantity 1, and we're going to multiply that by concentration 1, and that will equal quantity 2 times concentration 2. And when we know 3 out of the 4 variables, we'll be able to solve for the one that we need. And something to remember about this, the quantity units must match. So if it's a quantity of grams, both quantities have to be in grams, Q1 and Q2. And the concentration units must match. So if the concentration is in a percentage, they both must be a percentage. C1 and C2 both have to be a percentage. Or if they're in a strength like milligrams, they would both have to be milligrams. And the answers are going to be what units are used. So if we're solving for, we have a percent in C1 and we're solving for C2, percent will be what the answer units are. Now we'll look at some example questions about dilutions. We'll begin with question number 1, and this is part A. How many milliliters of a 5% stock solution are required to make 1 liter of a 0.5% solution? So first we're going to determine the known variables of the dilution formula. And our dilution formula is Q1 times C1 equals Q2 times C2. So for quantity 1, that's what we're going to be looking for because it's how many milliliters. The concentration of this is 5%. It's how many milliliters of a 5% stock solution. So Q1 times 5% equals, and for part 2 of the equation, it's 1 liter of a 0.5% solution. So our Q2 is going to be 1 liter, but since we're asking for how many milliliters, we'll put in 1,000 milliliters since 1 liter equals 1,000 milliliters. Because remember, our quantities must match in units. And so it would be 1,000 milliliters times 0.5%. Now we're going to solve for our unknown variable. In this case, it was Q1, quantity 1. So Q1 times 5 equals 1,000 times 0.5. 1,000 times 0.5 is 500, and then to solve for Q1, we're going to divide both sides by 5, so 500 divided by 5 equals 100. So Q1 equals 100 milliliters. So 100 is how many milliliters of the 5% stock solution are required to make 1 liter of the 0.5% solution. Now we'll look at part B of question 1. How much sterile water should be added to make the final product? So if you look at our question, you know we need a total of 1 liter, which is 1,000 milliliters for the final product. We know from part A, solving part A, that 100 milliliters will be the 5% stock solution. So now we need to determine the volume to add. And we'll do this by taking the total volume needed and subtract the stock solution needed, and that will give us the volume to add. So 1,000 milliliters minus 100 milliliters equals 900 milliliters. So we need 100 milliliters of the 5% stock solution, and then we'll need 900 milliliters of the sterile water, and that will make a total of 1 liter or 1,000 milliliters of the 0.5% solution. Question number 2. How many grams of 5% hydrocortisone ointment and ointment base must be combined to obtain 100 grams of 1% hydrocortisone ointment? So first we're going to determine the known variables of the dilution formula. So Q1, again, that's what we're looking for in this question as well, because it's how many grams. And the concentration is 5% that goes with part 1. So it'd be Q1 times 5%. And that equals Q2, which will be 100 grams of concentration 2, which is 1%. So 100 grams times 1%. So now we need to solve for our unknown variable, which in this case is Q1. So Q1 times 5 equals 100 times 1. 100 times 1 is 100. Then we'll divide by 5 for both sides to solve for Q1. And 100 divided by 5 equals 20. So Q1 will be 20 grams of 5% hydrocortisone ointment is what's needed for this. So now the other part of the question, it asks for how much hydrocortisone, the 5% hydrocortisone ointment, and also how much of the ointment base. So if we know we need 20 grams of 5% hydrocortisone, we're making a product that's a total of 100 grams. So we will take 100 grams minus our 20 grams, and that gives us 80 grams of the ointment base will be needed. So to prepare this, we will add 20 grams of the 5% hydrocortisone ointment, 80 grams of the ointment base, and that will give us a total of 100 grams of 1% hydrocortisone ointment. Question number 3. If you combine 30 grams of 5% lidocaine ointment with 15 grams of ointment base, what is the new percent strength? So this is a solid dilutions problem. So we're going to do it the same way. We're going to determine the known variables of the dilution formula. So Q1 times C1 equals Q2 times C2. So Q1 in this case is 30 grams, and our C1 is 5%. So 30 grams times 5%. And then Q2, that's going to be our total of our product, which we know we're putting 30 grams plus 15 grams. So our Q2 is going to be 45 grams here. So it'll be 45 grams times C2. So now we're going to solve for our unknown variable. In this case, it's C2. So 30 times 5 equals 45 times C2. 30 times 5 is 150. Then we divide both sides by 45 to give us what C2 equals. So 150 divided by 45 equals 3.3%. That will be our new percent strength of our final product of concentration 2. And you can see the reason that's percent is because it was percent for C2, or C1 was percent, so C2 also has to be percent. Just as we had Q1 was grams, Q2 also was grams. So you always make sure your units match for quantities, and then the units match for concentrations, and your answer will be in whatever those units are, whether you're solving for concentration or quantity. Okay, now we'll look at a summary and just some key points to remember about dilutions. Dilutions are drug products with increased volume. And when we have this increased volume, this is going to decrease the concentration, but the active drug ingredient remains the same. Some types of dilutions include liquid and solid. Liquid ones are generally in grams per milliliter. This includes solutions. Solid dilutions are generally in grams per gram. This includes creams and ointments. And our formula for solving dilution problems is Q1 times C1 equals Q2 times C2, where Q stands for quantity and C stands for concentration. And remember, our quantity units must match and our concentration units must match. And the answers are going to be in what units are used. And our steps for solving concentration questions: first, we'll determine the known variables of the dilution formula, and then we'll solve for the unknown variable. Thanks for watching. Please like and share this video with others who may find it helpful, and please subscribe to see more of my drug information videos. Thank you. Hi, my name's Amanda and I'm a pharmacist. Today I'm going to be talking about a type of pharmacy calculation called alligation. If you find this video helpful, please press the like button, subscribe to my channel, and share it with others who may find it helpful too. Thanks, I really appreciate it. So we'll begin with what is alligation. Alligation is a method for calculating the amounts of two concentrations of the same drug needed to make a different concentration from what is available. So alligation can be used for various products, including liquids and creams, and it's useful in compounding. And I'm going to give you an example just so you can see what I'm talking about. A prescription requires 100 milliliters of a 20% solution. You have 50% and 10% of that solution in stock. How much of each solution should be mixed to make 100 milliliters of 20% solution? So we'll solve this in a few minutes, but I just wanted to give you an example just so you can see exactly what I'm talking about. You have two concentrations of the same drug, and you're going to make a different concentration using those two that you have. So one concentration is stronger and one is weaker than the desired concentration in all alligation problems. So part of the difficulty in solving alligation calculations is being able to recognize them. To recognize an alligation calculation, number one, there will be two concentrations available, so two different strengths will be specified that are available. And number two, a different concentration is required to be made from those two concentrations that you have. So there are two methods for solving alligation calculations. I'll be covering both of these, and use the one that's easiest for you. There's the ratio method and the tic-tac-toe method. So first we'll look at the alligation ratio method. Step one, what we're going to do is identify the high concentration, which I'll refer to as HC, the low concentration, or LC, and the desired concentration, which I call DC. Step two, we'll subtract to obtain the ratio of HC to LC. So the desired concentration minus the low concentration will give us the high concentration ratio value. Then the high concentration minus the desired concentration will give us the low concentration ratio value. So we'll just put those in, the HC to LC, those numbers. And step three, we'll add the HC ratio value and the LC ratio value to determine the total number of parts. So that will give us the total number when we add those together. And step four, we're going to set up fractions and multiply by quantity needed, like this will be given in the problem, to obtain how much of each concentration is needed. So that's just an overview of the steps to do the ratio method. And now we'll look at the example that I gave you at the beginning, and we'll solve that using the ratio method. So the example was, a prescription requires 100 milliliters of a 20% solution. You have 50% and 10% of that solution in stock. How much of each solution should be mixed to make 100 milliliters of 20% solution? So step one, we're going to identify the high concentration, the low concentration, and the desired concentration. So HC is 50, LC is 10, and DC is 20. Now we're going to subtract to obtain the ratio of HC to LC. So the DC minus LC will be 20 minus 10, and that will give us 10. And then the HC minus the DC will give us the LC ratio value. That will be 50 minus 20, so that equals 30. So our HC to LC, our high concentration to low concentration ratio, will be 10 to 30, or you can reduce that to 1 to 3, but you don't have to reduce it. You could go with the 10 to 30, but I just reduced it to keep the numbers more simple. Okay, now in step 3, we're going to add the HC ratio value and the LC ratio value to determine the total number of parts. So our ratio is 1 to 3. So 1 part of high concentration to 3 parts of low concentration is what that ratio means. And so we'll add 1 plus 3, and that gives us a total of 4 parts. Now in step 4, we're going to set up a fraction and multiply by quantity needed, which will be given in the problem. In our problem, you can see it's 100 milliliters. It's how much of the final solution we need. And this will help us to obtain how much of each concentration is needed. Okay, so for our HC, our high concentration, the ratio value for it is 1. So our fraction will be 1/4 because there are 4 total parts, so 1 over 4. And then times 100 milliliters because that is our quantity. to be made. And if we do the math there, we do 1 times 100, then divided by 4, will give us 25 milliliters of the high concentration, which is the 50% solution. Then for the low concentration, our ratio value is 3. So 3 out of 4, 3/4, because 4 is the total parts, times 100 milliliters. So 3 times 100 is 300. Then divided by 4, that gives us 75 milliliters of the low concentration, which is the 10%. And you can see that the 25 milliliters and the 75 milliliters add up to 100 milliliters. So that would give us 100 milliliters of 20% solution if we mix 25 milliliters of 50% solution and 75 milliliters of the 10% solution. Okay, so now we're going to look at the alligation tic-tac-toe method. So step 1 with it, we're going to identify the high concentration, low concentration, and desired concentration. And we're going to place them at the correct location in a tic-tac-toe grid. So you can see where it gets its name. The high concentration is going to go in the top left. The desired concentration will go in the very center. And the low concentration goes in the bottom left. Now for step 2, we're going to find the differences diagonally. So we're going to find the difference between the high concentration and the desired concentration, and we're going to write that in the bottom right grid. Then we're going to find the difference in the low concentration and the desired concentration, and we'll write that in the top right grid. Next, we're going to add the differences vertically. So we'll add the difference between the low and the desired concentration with the difference between the high concentration and the desired concentration, and this will give us the total parts. Next, we're going to determine the fraction of each needed. So for the high concentration, this will be at the top. We have the difference between the LC and DC number that we have there. That will be our HC part. And then we will put that over the total part. So that will be our high concentration fraction. And then we'll do the same thing for the low concentration. We'll take the number we have there in the bottom right box. That's the difference between the high concentration and desired concentration. That's our low concentration part. And we'll put that over the total part. So that will give us our low concentration fraction. Now we're going to multiply each fraction by the quantity needed. Remember, this is given in the problem, and this will allow us to obtain how much of each concentration is needed. So we'll take our high concentration fraction, which is our high concentration part over our total concentration part, multiply that by the quantity needed. That will give us our amount of high concentration solution needed. Then we'll take, for our low concentration fraction, it's the low concentration part over the total part. We'll multiply that by the quantity needed. That will give us the amount of low concentration needed. So now we'll go through this with an example, the tic-tac-toe method. So we'll use the same example. A prescription requires 100 milliliters of a 20% solution. You have 50% and 10% in stock. How much of each solution should be mixed to make 100 milliliters of 20% solution? So first we're going to identify our high concentration, desired concentration, and low concentration, and we'll place them in the correct location in your tic-tac-toe grid. So remember, the high concentration goes in the top left corner, the desired concentration goes in the center, and then the low concentration goes in the bottom left. Now we're going to find the differences diagonally. So with the high concentration, the difference between 50 and 20 will give us 30, and we'll put that in the bottom right. And then diagonally for the low concentration, the difference between 10 and 20, that gives us 10, and we'll put that in the top right. Next, we're going to find the total parts, and we'll do this by adding the differences vertically. So we have 10 plus 30, and that gives us 40. So 40 is our total parts. Now we're going to determine the fraction of each needed. So for the high concentration, it's 10 parts out of 40 is our total parts. So our high concentration fraction is 10 out of 40. And for the low concentration, we have 30 parts out of the total 40 parts. So it's 30 out of 40. Now we're going to multiply each fraction by the quantity needed. That's given in our problem, which is 100 milliliters in this problem. And this will allow us to obtain how much of each concentration is needed. So our high concentration fraction was 10 out of 40. So times 100 milliliters. So you can do that. 10 times 100, which is 1,000, divided by 40 equals 25 milliliters of the 50% solution. That's our high concentration. And then the low concentration fraction was 30 out of 40. So 30 times 100, that gives us 3,000 divided by 40. That equals 75 milliliters. So that we'll need 75 milliliters of the low concentration solution, which is the 10% solution. And you can see we got the same exact answer, just a little bit different methods of doing it. But you can see you add the 25 milliliters and the 75 milliliters, and that gives us 100 milliliters total. And that will, of 25 milliliters of the 50% solution plus 75 milliliters of the 10% solution, that will give us 100 milliliters of 20% solution. So now we'll just go over a summary and some key points to remember. Remember, alligation is a method for calculating the amounts of two concentrations from the same drugs needed to make a different concentration from what's available. One concentration is stronger or higher. I refer to this as HC. And one is weaker or lower. This will be LC, low concentration, than the desired concentration, which is DC. And alligation problems can be solved using the ratio method or the tic-tac-toe method. Use the one that makes the most sense for you. And both alligation methods are ways to determine the amounts of the high concentration and low concentration needed to make the desired concentration. Just a summary of the ratio method steps. You're going to identify the high concentration, low concentration, and desired concentration from the problem. Subtract to obtain the high concentration to low concentration ratio. And to get this, you'll take the DC minus the LC. That will give you the HC ratio value. Then you'll take the HC minus the DC, and that will give you the LC ratio value. Next, you'll add the HC and LC ratio values to obtain the total parts, and then set up fractions and multiply by the quantity needed. So you'll set up a fraction with the low concentration ratio value over the total parts and multiply that by the quantity needed. That will give you your low concentration quantity amount. And then for the high concentration ratio value over the total parts times the quantity needed, that will give you your high concentration quantity amount. And then a summary for the tic-tac-toe method. First, you'll identify the high concentration, low concentration, and desired concentration and place them in the correct location in the tic-tac-toe grid. Remember, the high concentration goes in the top left, the desired concentration goes in the center, and the low concentration goes in the bottom left. Then you're going to find the differences diagonally, write those numbers in the grid, then add the different parts, add the differences vertically to get the total parts. And then you'll determine the fraction of the high concentration, which will be across the top, and the low concentration, which will be on the bottom. And you'll just put the high concentration amount over the total parts and the low concentration amount over the total parts. That will give you those fractions. And then multiply each fraction by the quantity needed, which, like I said before, it's specified in the problem. Thanks for watching. Please like and share this video with others who may find it helpful, and please subscribe to see more of my drug information videos. Thank you. Hi, my name's Amanda and I'm a pharmacist. Today I'll be talking about a type of pharmacy calculation called IV flow rates. And if you find this video useful, please press the like button and subscribe to my channel and share it with others who may find it helpful too. Thanks, I really appreciate it. So we'll begin with what are flow rates. A flow rate is the volume per time that a medication is delivered by intravenous or IV route to a patient. It's also known as a drip rate or infusion rate. So you can see flow rate equals volume per time. So volume, this is for liquid measurements. It can be liters, milliliters, or drops. time, this is a time measurement such as hours or minutes. And just to show you some examples of some common flow rate units, there could be milliliters per hour or drops per minute. And there you see it's volume per time. So now we'll talk a little bit about IV administration sets. IV administration sets, or IV sets, deliver IV solution to the patient by connecting to the IV bag. IV sets work by either a gravitational drip chamber, you can see this in photo 1, or an electronic infusion pump. And this is an example in photo 2. Electronic pumps, they can be set at various flow rates. But with a gravitational drip chamber IV set, they have different drop factors that are used in flow rate calculations. Now we'll talk a little more about that. A drop factor, or also known as a drip factor, is the number of drops it takes to have a volume of 1 milliliter. So the drop factor units are drops per ml, or if you remember in our abbreviations, drops is abbreviated GTTS, so GTTS per ml. There are different IV sets that have different drop factors. There's what's known as macro sets, and macro means large, so you can think of these as having a large amount with each drop. For example, 10 drops per milliliter. It would only take 10 drops to make 1 milliliter. And then there are micro sets, and micro means small. So you can think of these as having a small amount with each drop. So an example would be 60 drops per milliliter. The drops are small, so it's going to take more drops for 1 milliliter. In this case, 60 drops. Now we'll talk about solving flow rate calculations. Flow rate calculations can be solved by using conversions and ratio and proportion calculations. And it's important that you know the common conversions. Conversions that are often seen in flow rate calculations include volume, time, and dosage ones. And here I have a table that shows some of the common conversions for flow rate calculations. Liters to milliliters, so 1 liter equals 1,000 milliliters. Hours and minutes, 1 hour equals 60 minutes. Grams with milligrams, 1 gram equals 1,000 milligrams. And milligrams with micrograms, 1 milligram equals 1,000 micrograms. Now we'll look at the steps for solving flow rate calculations. First, you want to identify the unit or units the problem is asking for. This could be just a single unit such as milliliters or hours, or it could be multiple units such as milliliters per hour. Next, you want to use the other information in the problem to get the units needed. And there are 2 methods for this. And if you've seen any of my other pharmacy calculations videos, you'll recognize these methods are from my conversions video. So it's the same exact methods. Method number 1, you can set up fractions that cancel like units, leaving the desired units only, then multiply the fractions. So for example, if we're trying to convert 5 hours into minutes here, we know there are 60 minutes per 1 hour times 5 hours over 1. We have an hour on the top, an hour on the bottom, so those units cancel. We're left with minutes, and then we just multiply the fractions. So 60 times 5 is 300, then divided by 1 times 1, which is 1. That gives us 300 minutes. Or we can use method 2. Set up equivalent fractions, cross multiply, then divide to solve for x. So for this example, we'll use the same example as the 5 hours, converting it to minutes. So there are 60 minutes per 1 hour, and we'll set that equal to x minutes per 5 hours. And notice with these you have to have the same units on the top and the same units on the bottom. So we have minutes on the top, hours on the bottom. So 60 times 5, that's our cross multiplication, is 300. Then we'll divide by 1. That gives us 300, and that solves for x. So x here is 300 minutes. And you can use whichever method makes the most sense for you, or whichever method makes the most sense for the problem that you're solving. Okay, now we'll look at some examples of flow rate calculations. This is example 1, and I'm going to work through both methods with all of our examples so you can see multiple ways to do these calculations. So this is with method number 1. So our order is for 1200 milliliters of NS, and NS stands for normal saline. This is 0.9% sodium chloride solution. So 1200 milliliters of normal saline to be infused over 8 hours. How many milliliters will be infused every hour? So first we're going to identify our units the problem's asking for. And here it's milliliters. So with method 1, we'll set up our fractions that cancel like units, then multiply the fractions. So we can know there's 1200 milliliters per 8 hours. Milliliters is the unit that we're wanting. And then times 1 hour. We want to know how many milliliters for every hour. So it'll be 1 hour over 1. We have an hour on the top, an hour on the bottom, so the hours cancel. We're left with milliliters. And if we do the math, 1200 times 1 is 1200 divided by 8 times 1, which is 8. That gives us 150 milliliters. And if you're using method 1, if there's only one unit that you're trying to solve for, make sure it's on top. That will make sure that you get the correct answer. And just remember, for units to cancel, you must have it one unit on the top and one on the bottom. That's how they'll cancel. And to make a fraction that has only one unit, you just put a 1 with it. And that can be either on the top or the bottom. In this case, it was on the bottom. Okay, now we'll look at the same example with method number 2. So example number 1 with method number 2. So our order was for 1200 milliliters of normal saline to be infused over 8 hours. How many milliliters will be infused every hour? So here we're looking for milliliters. And with method 2, we're going to set up equivalent fractions, cross multiply, then divide to solve for x. So we know there's 1200 milliliters per 8 hours. And we'll set that equal to x milliliters per 1 hour. And where x here, it's the variable representing the answer we're looking for. And our unit of the top fractions, which those are numerators, they have to match, and they do. They're both milliliters. And the unit of the bottom fractions, which are denominators, those must match, and they do. They're both hours. So now we'll just cross multiply, then divide to solve for x. So 1200 times 1 equals 1200, and then we'll divide by 8 to solve for x. So 1200 divided by 8 equals 150 milliliters. Okay, now we'll look at example number 2 with method number 1. So it's a very similar problem here. We have 1200 milliliters of normal saline to be infused over 8 hours. How many milliliters will be infused every 10 minutes? So we're looking again for milliliters, but instead of for every hour, we're going to find for every 10 minutes. So with method 1, we'll set up our fractions that cancel like units, then multiply the fractions to get the answer. So we have 1200 milliliters per 8 hours times 1 hour per 60 minutes. And we have an hour on the top, an hour on the bottom, so those cancel. And then we have going to multiply that by 10 minutes over 1. So now our minutes will cancel. We have a minute on the top, a minute on the bottom. Those cancel, and we are left with what we want, milliliters. So now we'll just do the math. 1200 times 1 times 10 equals 12,000. And then divided by 8 times 60, which is 480. So 12,000 divided by 480 equals 25 milliliters. Okay, now we'll look at the same example with method number 2. So 1200 milliliters of normal saline to be infused over 8 hours. How many milliliters will be infused every 10 minutes? So we're looking for milliliters here. And with method 2, we'll set up equivalent fractions, cross multiply, then divide to solve for x. So we know 1200 milliliters, and we're going to set that over 480 minutes. And in the rectangular box here, I have how I converted the 8 hours into 480 minutes. So 1 hour equals 60 minutes. And then there are 8 hours here, so 8 hours times 60, that equals 480 minutes. So we have 1200 milliliters over 480 minutes. and we'll set that equal to X milliliters over 10 minutes. So 1200 times 10, so our cross multiplying equals 12,000, and then we'll divide by 480 to get X, and that equals 25 milliliters. Okay, now we'll look at example number 3 with method number 1. Our order is for 500 milliliters of D5W, and D5W, that means dextrose 5% in water solution. So 500 milliliters of D5W to be infused over 6 hours. What is the flow rate in drops per minute? And drip rate equals 60 drops per milliliter. So if we identify our units the problem's asking for, it's drops per minute. So with method 1, we know our drip rate is 60 drops per milliliter. We'll multiply that by 500 milliliters per 6 hours. So we have a milliliter on the top and a milliliter on the bottom, and those cancel. And then we know there's 1 hour per 60 minutes, so we'll multiply that by 1 hour over 60 minutes. So we have an hour on the top, an hour on the bottom, and those cancel. And we're now left with our drops on the top and minutes on the bottom. So that will give us the correct answer once we do the math. So 60 times 500 times 1, that equals 30,000, divided by 6 times 60, that's 360, and that gives us 83.3, and we'll round that to 83, so it's 83 drops per minute. Okay, now we'll look at example number 3 with method number 2. Our order is 500 milliliters of D5W to be infused over 6 hours. What is the flow rate in drops per minute? And our drip rate is 60 drops per milliliter. So if we identify our units, we're looking for drops per minute. And with method 2, we'll set up equivalent fractions, cross multiply, then divide to solve for X. So we have 60 drops per 1 milliliter, that's our drip rate, and we'll set that equal to X drops per 500 milliliters. So this will give us the first unit, our drops with this one. So 60 times 500 equals 30,000, and then divided by 1, that gives us 30,000, so it's 30,000 drops. Now we need to look at the time part of this. We know 1 hour equals 60 minutes, and this is for 6 hours. So 6 hours times 60 would be 360 minutes. So we'll take 30,000 drops divided by 360 minutes, and that gives us 83 drops per minute. Okay, now we'll look at example number 4 using method 1. So our order is for 1 liter of D5W to be infused over 6 hours. If using a 10 drop per milliliter IV set, how many drops per minute will be delivered to the patient? So we'll identify our units the problem's asking for, and this is drops per minute. And with method 1, we'll set up our fractions that cancel like units, then multiply the fractions. So we know 1 liter equals 1,000 milliliters. So we'll start with that. 1,000 milliliters per 1 times 10 drops per 1 milliliter times 1 hour per 60 minutes times 1 over 6 hours. And this cancels milliliters. Cancel. We have a milliliter on the top, milliliter on the bottom. We have an hour on the top, an hour on the bottom. And that leaves us with our units we want, drops per minute, drops on the top, minutes on the bottom. So we'll do the math. 1,000 times 10 times 1 times 1 would be 10,000. And then we'll divide that by 1 times 60 times 6, which would be 360. And that gives us 27.8 drops per minute. And we'll round that to the nearest number, which would be 28 drops per minute. Okay, now we'll look at the same example 4 with method number 2. So our order is for 1 liter of D5W to be infused over 6 hours. If using a 10 drop per milliliter IV set, how many drops per minute will be delivered to the patient? So we're looking for drops per minute, and with method 2, we'll set up our equivalent fractions, cross multiply, then divide to solve for X. So 10 drops per 1 milliliter equals X drops per 1,000 milliliters, because we know that 1 liter equals 1,000 milliliters. We can go ahead and do that. So if we cross multiply and divide, we have 10 times 1,000 equals 10,000 divided by 1. That gives us 10,000 drops. So that's the top part of our unit. Now we have to find the other part, the minutes. So 1 hour equals 60 minutes, and there are 6 hours here, so 6 hours times 60, that's 360 minutes. So now we take 10,000 drops divided by 360 minutes, and that equals 27.8 drops per minute, and we'll round that to 28 drops per minute. Okay, we'll look at one more example here. Example 5 with method number 1. Our order is for vancomycin 1.5 grams per 500 milliliters at 10 milligram per minute rate. How long would it take to deliver the medication at the correct rate? So I have a note about IV vancomycin here. It is a medication that must be administered slowly at a rate no faster than 1 gram per hour or 10 milligrams per minute to prevent an adverse reaction called vancomycin flushing syndrome, or VFS. So this causes redness in the face and the upper body. So it has to be administered slowly. That's something important to know about vancomycin. I just thought I'd put that in there since we had an example about vancomycin. So back to our problem. We want to identify the units the problem's asking for. Here we don't have a specific unit, it's just how long. So it's time, so it's either going to be minutes or hours. So with method 1, we can set up fractions that cancel like units, then we'll multiply the fractions. So our rate it's 10 milligrams per minute. Well, we want time, so we're going to put minutes on the top. So we're going to say 1 minute per 10 milligrams. And that will be times 1,000 milligrams per 1 gram, because our dose is given in grams, but we have to have milligrams for it to be able to cancel. And then times 1.5 grams over 1. So that leaves us with minutes on the top. We have a milligram on the top and a milligram on the bottom, and those cancel. And then we have a gram on the top and a gram on the bottom, and those cancel. And that equals 150 minutes when we do the math. 1 times 1,000 times 1.5, and divide that by 10 times 1 times 1. That gives us 150 minutes. Well, we know there are 60 minutes in 1 hour, so if we take 150 and divide it by 60, that will give us how many hours? So it would be 2.5 hours. Okay, now we'll look at example number 5 with method number 2. So we have vancomycin 1.5 grams per 500 milliliters at 10 milligram per minute rate. How long would it take to deliver the medication at the correct rate? So identify our units. It's asking how long, so this is going to be time, either minutes or hours. And with method 2, we'll set up equivalent fractions, cross multiply, and then divide to solve for x. So we'll get our milligrams first. So 1,000 milligrams per 1 gram equals x milligrams per 1.5 grams. And if we cross multiply and divide, we get 1,000 times 1.5 divided by 1. That gives us 1,500 milligrams. So now we can set that up with our rate to solve for our time. So 1,500 milligrams per x minutes, that's what we're solving for, equals 10 milligrams per 1 minute. So if we have 1,500 times 1 is 1,500 divided by 10, that gives us 150 minutes, or when we divide by 60, that gives us 2.5 hours. So now we'll look at a summary and key points about IV flow rates. So a flow rate is the volume per time that a medication is delivered by IV route to a patient. It's also known as a drip rate or infusion rate. There are IV sets that have different drop factors, and these are in drops per milliliter, that can be used in flow rate calculations. Flow rate calculations can be solved with conversions and ratio and proportion calculations, and there are 2 methods. Method 1, we set up fractions that cancel like units and then multiply to get our answer. Method 2, you can set up equivalent fractions, cross multiply, and then divide to solve for x. Thanks for watching. Please like and share this video with others who may find it helpful, and please subscribe to see more of my drug information videos. Thank you. Hi, my name's Amanda and I'm a pharmacist. Today I'll be talking about a type of pharmacy calculation called temperature conversions. And if you find this video useful, please press the like button, subscribe to my channel, and share it with others who may find it helpful too. Thanks, I really appreciate it. So first we'll begin just talking about temperature measurements. There are two temperature scales, the Fahrenheit and Celsius scale, and both are measured in degrees. So you have degrees Fahrenheit or degrees Celsius. Fahrenheit is used in the United States as the standard temperature measure. Celsius is the metric system measurement of temperature. It's used in science because its scale is shaped around when a reaction will take place. So for example, 0 degrees Celsius equals the temperature that water freezes. In Fahrenheit, this is 32 degrees. And 100 degrees Celsius is the temperature that water boils. In Fahrenheit, this is 212 degrees. So you can see that those are easy numbers to remember because that's when reactions occur. Now we'll talk a little bit about Fahrenheit versus Celsius. Fahrenheit temperatures are typically much higher than equivalent Celsius temperatures, but differences get smaller the lower you go in temperature. And I have a chart here that shows the common Fahrenheit and Celsius equivalents. And these are good to know just so you have an idea of the differences between the Fahrenheit and Celsius temperatures. The boiling point of water is 212 degrees Fahrenheit. It's 100 degrees Celsius. Normal body temperature is 98.6 degrees Fahrenheit. It's 37 degrees Celsius. Controlled room temperature, it's 68 to 77 degrees Fahrenheit, or 20 to 25 degrees Celsius. Many times drugs are specified to be stored at controlled room temperature. Freezing point of water is 32 degrees Fahrenheit, or 0 degrees Celsius. And parity, this is the point at which the two temperature units are equal. Parity for Fahrenheit and Celsius is negative 40. So this means negative 40 degrees Fahrenheit equals negative 40 degrees Celsius. That's the point at which they are equal. Now we'll talk about the temperature conversion formulas. So Fahrenheit and Celsius units are not proportionate, so conversions require a formula. You can't just do a ratio calculation with these because their units are not proportionate. So there are two formula types. There are plug-in formulas or an algebra formula. And the best thing to do is just to choose the formula that's easiest for you because these formulas have to be memorized. So the plug-in formulas for Fahrenheit and Celsius conversions, there are two of them. Celsius times 1.8, and that's in parentheses, so it means you do that part first, plus 32, that will give you the degrees Fahrenheit. And then to calculate the degrees Celsius, you take the Fahrenheit temperature minus 32, and that's in parentheses, so that means you do that first, then divided by 1.8. So that will give you the degrees Celsius. Then the algebra formula for Fahrenheit to Celsius, it's a little simpler to remember as long as you know how to do the algebra part of the math. 5F equals 9C plus 160. And those can be a little difficult to remember, so I have some memorization tips, just depending on which ones you choose to memorize. But like I said, these formulas have to be memorized, and choose what's easiest for you. So for the plug-in formulas, if you memorize one, the other is backward and opposite. So if we look at these here again, the degrees Fahrenheit is going to equal Celsius times 1.8 plus 32. So then we look at the one for finding Celsius. It equals Fahrenheit minus 32, so you can see that's backward and opposite, then divided by 1.8. Once again, it's backward and opposite. And if you choose to do the algebra formula, you can remember it a little easier by remembering that 5 starts with F. So it's FF at the beginning. 5F equals 9C plus 160. Now we'll look at some examples, and so you can see how to work these problems. So the first example is convert 100 degrees Celsius to degrees Fahrenheit. So if we use the plug-in formula, we're going to take the degrees Celsius times 1.8 plus 32, and that will give us the degrees Fahrenheit. That's our formula. So we have 100 times 1.8, and that's in parentheses, so we do that part first. That equals 180. Then plus 32. 180 plus 32 is 212, so that equals our degrees Fahrenheit. So 100 degrees Celsius equals 212 degrees Fahrenheit. Now we'll look at the same example but using the algebra formula. So convert 100 degrees Celsius to degrees Fahrenheit. We have 5F equals 9C plus 160 is our formula. So we'll just plug in our Celsius temperature here. So we have 5F equals 9 times 100 plus 160. So we do what's in parentheses first. 9 times 100, that will be 900. Then plus 160, that gives us 1060. So 5F equals 1060. And then in algebra, what we do to one side, we have to do to the other. So we want to get our F by itself. So in order to do that, we're going to divide by 5. So because 5 divided by 5 equals 1, and 1F, we can just simplify that and say F. So 5F divided by 5, that will give us F. What we do to one side, we have to do to the other. So we have 1060 divided by 5, and that equals 212. So F, our degrees Fahrenheit, will be 212. 100 degrees Celsius equals 212 degrees Fahrenheit. Now we have example number 2. Convert 12 degrees Celsius to degrees Fahrenheit. And first we'll look at our plug-in formula. We're using the same one on this because we're finding Fahrenheit again. So degrees Celsius times 1.8 plus 32. That will give us our degrees Fahrenheit. So we just plug in the 12 for the degrees Celsius. So 12 times 1.8, we keep that in parentheses, means we do that first, plus 32 equals our Fahrenheit degrees. So 12 times 1.8 equals 21.6 plus 32, and that equals 53.6, and that will round up to 54 degrees. So 12 degrees Celsius equals 54 degrees Fahrenheit. Now we'll look at the same problem with the algebra formula. So convert 12 degrees Celsius to degrees Fahrenheit. And our algebra formula is 5F equals 9C plus 160. So 5F equals 9 times 12, then plus 160. So 9 times 12 is 108, and then plus 160 is 268. So now we have it to 5F equals 268. We have to get F by itself, so we're going to divide by 5. Remember what we do in algebra, what we do to one side, we do to the other. So 5F divided by 5 will leave us with F, and then 268 divided by 5 will give us 53.6. So the Fahrenheit degrees is 53.6, round that to 54 degrees, so 12 degrees Celsius equals 54 degrees Fahrenheit. Now we'll look at example number 3. Convert 86 degrees Fahrenheit to degrees Celsius. So here we need our other plug-in formula because we're converting to degrees Celsius. So it's degrees Fahrenheit minus 32, or that's in parentheses, divided by 1.8. So we'll just plug in our Fahrenheit number. 86 minus 32 equals 54. Then divided by 1.8 gives us 30. So that's our degrees Celsius. So 86 degrees Fahrenheit equals 30 degrees Celsius. And now we'll look at the same example with our algebra formula. Convert 86 degrees Fahrenheit to degrees Celsius. So our algebra formula is 5F equals 9C plus 160. So 5 times 86 equals 9C plus 160. So we're plugging in for our Fahrenheit there. So 5 times 86 is 430. And then we have 430 equals 9C plus 160. Remember in algebra, what we do to one side, we have to do to the other. So we're trying to get our C by itself. So first thing we're going to do is we have to subtract 160 off of each side. So if we take 160 off, 430 minus 160 equals 270 equals 9C. So now we've got the 160 off, so now we have to get the 9 off Celsius, and in order to do that, we're going to divide by 9 on both sides. So 9 Celsius, 9C divided by 9 will be 1C, so we can just write C, and then 270 divided by 9 is 30. So our degrees Celsius is 30. So 86 degrees Fahrenheit equals 30 degrees Celsius. And we'll do one more example, example number 4. Convert 110 degrees Fahrenheit to degrees Celsius. So with our plug-in formula, we have degrees Fahrenheit minus 32, that's in parentheses, divided by 1.8. That will give us our degrees Celsius. So we plug in our Fahrenheit number, we have 110 minus 32, that equals 78. Then divided by 1.8 equals 43.3, that's our degrees Celsius. So 110 degrees Fahrenheit equals 43 degrees Celsius. And now we'll look at that same example with our algebra formula. So convert 110 degrees Fahrenheit to degrees Celsius. So our algebra formula is 5F equals 9C plus 160. So we just plug in our number here. We have our degrees Fahrenheit, and we're going to be solving for C, our degrees Celsius. So 5 times 110 equals 9C plus 160. 5 times 110 is 550, and that leaves us with 550 equals 9C plus 160. So now we're going to subtract 160 off each side, and that will leave us with 550 minus 160, which is 390, equals 9C. Divide both sides by 9 to get our C by itself. 390 divided by 9 is 43.3, and that equals C. So that's our Celsius. So 110 degrees Fahrenheit equals 43 degrees Celsius. Now we'll just look at a summary and some key points about temperature conversions. Fahrenheit and Celsius degrees are not proportionate, so conversions require a formula. Remember, this isn't just a simple ratio calculation. And they're the plug-in formulas or the algebra formula. And just do this the method that's easiest for you. And remember, these formulas have to be memorized, so choose the method that's easiest to memorize that formula. So the plug-in formulas for conversion are degrees Celsius times 1.8 in parentheses plus 32 equals degrees Fahrenheit, and degrees Fahrenheit minus 32 in parentheses divided by 1.8 equals degrees Celsius. And remember, when it's in parentheses, that just means you do that part first. And a way to remember these is that they are exactly backward and opposite each other. And the algebra formula for conversions, remember, is 5F equals 9C plus 160. And you just solve for the variable that you need. And when you can remember that by remembering 5F, it's FF. 5 starts with F, and that goes with the F. So thanks for watching. Please like and share this video with others who may find it helpful, and please subscribe to see more of my drug information videos. Thank you. Hi, my name's Amanda and I'm a pharmacist. Today I'll be talking about weight-based dosage calculations. And if you find this video useful, please press the like button, subscribe to my channel, and share it with others who may find it helpful too. And if you'd like to support this channel with a donation, press the heart thanks button to give me a super thanks. Thanks, I really appreciate it. So for some medications, the amount of drug to be given to a patient depends on the patient's weight. Most medications for children are dosed based on weight due to the extreme differences in patient size. And this makes sense. Typically, the smaller the patient size, the smaller the dose will be needed. The greater the patient size, the greater the dose will be needed. There are also some adult medications that are dosed based on weight due to characteristics of the particular drug being given. Some characteristics of drugs that require weight-based dosages for adult medications include drug distribution. This is how a drug is transferred to the tissues of the body. For example, if a drug is fat-soluble. The greater the patient weight, the higher the dose is typically needed for fat-soluble drugs to reach appropriate concentrations in the body. And another characteristic is the therapeutic index. This is the ratio between the toxic dose and the effective dose. With a narrow therapeutic index drug, or an NTI drug, a small change in dose equals a large change in effect. Now we'll talk about how to solve weight-based dosage calculations. So first, weight-based dosages are typically specified in milligrams per kilogram or milligrams per kilogram per day. So to solve weight-based dosage calculations, first you want to determine the patient's weight in kilograms. And our conversion equivalent for this is 1 pound equals 2.2 kilograms. So basically what we're going to do on this, we'll divide the pound weight by 2.2. That will give us the weight in kilograms. Next, we'll determine the patient's dose. This is done by multiplying their kilogram weight by the milligram per kilogram dose. And then we'll determine the amount per dose, if it's in milligrams per kilogram per day. And to do this, we'll divide the total daily dose by the number of doses per day. And now we'll look at each of these steps in more detail. So first we'll look at how to convert a patient's weight from pounds to kilograms. So many weight-based dosages are specified in milligrams per kilogram or milligrams per kilogram per day of the medication. So when a patient's weight is given in pounds, it must be converted to kilograms. And our weight conversion equivalent is 1 kilogram equals 2.2 pounds. So in order to convert a patient's weight from pounds to kilograms, we can divide it by 2.2. You can memorize it just that and do it that way. Or if you just want to memorize the conversion equivalent, you can also set up fractions that cancel like units and multiply to get your answer. So I have an example of that here. If we have a 150 pound patient, there's 1 kilogram per 2.2 pounds times 150 pounds over 1. So you have a pound on the top, pounds on the bottom, those cancel, you're left with kilograms. Then you just do the math. 1 times 150 is 150, then divided by 2.2 times 1. It gives us 68.2. Or as I said, if you just take 150 divided by 2.2, 68.2 kilograms. So once the weight has been converted to kilograms, the amount of drug to be given can be obtained. And as I said, weight-based dosages are usually specified in milligrams per kilogram or milligrams per kilogram per day. So to obtain the dose, you can simply just multiply the weight in kilograms by the milligram per kilogram dose. So if you have a 68.2 kilogram patient and a dose of 5 milligrams per kilogram, we can just multiply 68.2 times 5. That will give us our milligram dose. Or if you want to set up the fractions that cancel like units, you can do it that way too, just so you can see how the units cancel, and it's a good double check on yourself. So 68.2 kilograms over 1 times 5 milligrams per kilogram. You have a kilogram on the top, kilogram on the bottom, those cancel. You're left with milligrams, so then you just do the math. 68.2 times 5 divided by 1. That would equals 341 milligrams. So if the dosage is specified in milligrams per kilogram per day and the directions are not QD, that's once a day, then the amount per dose may also need to be calculated. So to calculate the amount per dose, divide the total daily dose by the number of doses per day. So we'll continue with our example. We have 5 milligram per kilogram per day, and that equaled 341 milligrams per day, and we'll say that's given Q6 hours. Q6H is Q6 hours. So Q6H, we have 24 hours in a day divided by 6 hours. That would be 4 doses per day. So if we take 341 and divide it by 4, that equals 85.25 milligrams. So the patient would receive 85 milligrams Q6H. So 85 milligrams would be the amount per dose. So sometimes the dosage is specified in milligrams per kilogram and the frequency is stated with the dose, so the amount per dose is already determined. So for example, we have our 68.2 kilogram patient to be given 5 milligrams per kilogram Q6 hours. If you just do the math, the 5 milligrams per 1 kilogram times 68.2 kilograms over 1, we cancel a kilogram on the top, kilogram on the bottom, we're left with milligrams. 5 times 68.2 is 341, and that's 341 milligrams Q6H, because our amount is already determined, our dose is already determined. The 5 milligrams per kilogram is every 6 hours. So now we're going to look at some examples. So example 1, a 176-pound patient is to be given Lovenox 1.5 milligram per kilogram SQ/QD. What is the patient's total daily dose? So the medication we're working with here is Lovenox. Its generic name is enoxaparin, and it's a low molecular weight heparin blood thinner to treat or prevent blood clots. So we're giving it 1.5 milligrams per kilogram SQ/QD. SQ stands for subcutaneously, that means under the skin, and QD is once every day. So we're wanting the patient's total daily dose. So since it's once a day, we just figure out our milligram per kilogram dose, and that will be the amount given for the day. So 1 kilogram equals 2.2 pounds. So there's 1 kilogram per 2.2 pounds times 176 pounds over 1. Our pounds cancel, one's on the top, one's on the bottom, so they cancel. We're left with kilograms. So 176 divided by 2.2 equals 80 kilograms. And then we're given the dose of 1.5 milligram per kilogram times 80 kilograms over 1. Kilogram on the top, kilogram on the bottom, those cancel. We're left with milligrams. That gives us a total of 120 milligrams. So that is our total daily dose since it's administered once a day. Now example number 2. A 148-pound patient is to receive vancomycin 10 milligram per kilogram IV Q12H. What is the amount to be given for each dose? So our medication here is vancomycin. It's a glycopeptide antibiotic that's used to treat a variety of serious infections. It's given IV, and it's one that is dose-based according to weight and also other factors such as a patient's renal function. So we're given vancomycin 10 milligram per kilogram IV Q12H, so that's every 12 hours, and we're wanting to know what the total amount is to be given for each dose. So we have 1 kilogram equals 2.2 pounds, so we have to figure out how much the patient weighs in kilograms first. So 1 kilogram per 2.2 pounds times 148 pounds over 1. So 1 times 148 is 148 divided by 2.2 is 67 kilograms. So that's the patient's weight in kilograms. And then our dose is 10 milligrams per kilogram times 67 kilograms. We're left with milligrams, a kilogram on the top, kilogram on the bottom, those cancel. So 10 times 67 is 670 milligrams for each dose. So since it says it's 10 milligram per kilogram every 12 hours, that is the amount for each dose. It's already, we don't have to determine how many doses in the day. So example number 3. A child is prescribed cephalexin 75 milligrams per kilogram per day given QID. The child weighs 30 pounds. What amount of cephalexin will be given per dose? So cephalexin, this is an antibiotic that's a cephalosporin. And so we have 75 milligram per kilogram per day QID. QID is 4 times a day. So first we have to convert the child's weight into kilograms. So 1 kilogram per 2.2 pounds times 30 pounds. 30 divided by 2.2 is 13.6 kilograms. So now we have a dose of 75 milligrams per kilogram, and that's going to be per day. So 75 milligram per kilogram times 13.6 kilograms. We're left with milligrams on the top, kilogram on the top, a kilogram on the bottom, those cancel. 75 times 13.6 is 1,020 milligrams. So that is the total dose per day. So this is given QID, so 4 times a day. So we're going to divide that by 4 to get the amount per dose. So 1,020 divided by 4 equals 255 milligrams per dose. Okay, now we'll look at our last example, example number 4, and it has 3 parts. So a child is to receive amoxicillin at a dose of 50 milligram per kilogram per day. What is the total daily dose if the patient weighs 21 pounds? Then the dose of amoxicillin is to be given Q12H. How many milligrams should be given per dose? And then part C, if amoxicillin 400 milligram per 5 ml is dispensed, how many milliliters should be given per dose? So we'll look at part A first. So a child is to receive amoxicillin at a dose of 50 milligram per kilogram per day. What is the total daily dose if the patient weighs 21 pounds? So amoxicillin, that's an antibiotic in the penicillin class. We're dealing with it at a dose of 50 milligram per kilogram per day. So we're looking for the total daily dose if the patient weighs 21 pounds. So 1 kilogram equals 2.2 pounds. So 21 pounds divided by 2.2, that equals 9.5 kilograms. Then we have a dose of 50 milligram per kilogram. So 50 times 9.5 equals 477 milligrams. So that is our total daily dose, 477 milligrams. Part B, the dose of amoxicillin is to be given Q12H. How many milligrams should be given per dose? So Q12H means every 12 hours. So 24 hours divided by 12 hours, so that would be 2 doses. So the total daily dose was 477 milligrams. If we divide 477 by 2, that equals 239 milligrams per dose. So now we'll look at Part C. If amoxicillin 400 milligram per 5 milliliters is dispensed, how many milliliters should be given per dose? So this one, we know we need 239 milligrams per dose. So the way we'll do this is we're going to set up equivalent fractions, cross multiply, and then divide. So if there are 400 milligrams per 5 milliliters, we'll set that equal to 239 milligrams per X milliliters. So we're solving for X. So if we take 5 times 239, that equals 1,195. Then divide to solve for X, divided by 400 equals 2.99. We'll round that to 3, so it will be 3 milliliters would give us 239 milligrams, and that would be the amount that the patient should take per dose. Okay, so now we'll just look at a summary and some key points to remember. So weight-based dosages are typically specified in milligram per kilogram or milligram per kilogram per day. To solve weight-based dosage calculations, first determine the patient's weight in kilograms. Remember, 1 pound equals 2.2 kilograms. And a shortcut to do this, you can just divide the pound weight by 2.2. Or if you want to set up the fractions that cancel like units, you can do that as well, just so you can see exactly what's going on. Next, you determine the patient's dose. So we can do this by multiplying the kilogram weight by the milligram per kilogram dose. And then determine the amount per dose if the milligram per kilogram, if it's in a milligram per kilogram per day. And to do this, we'll divide the total daily dose by the number of doses per day. Thanks for watching. Please like and share this video with others who may find it helpful. And please subscribe to see more of my pharmacy learning videos. And if you would like to support this channel with a donation, press the heart thanks button to give me a super thanks. Thanks, I really appreciate it.